Hello, class. So this is the last lesson for this course. That is lesson 10. And in lesson 10, we only have three sections. 10.1 is writing exponential models. 10.2 is doubling time or halving time. And 10.3 is exponential regression. So these are the three things we are going to be looking at in lesson 10. Now, let's start with 10.1. Now, we want to go back to characteristics of exponential functions, which we did look at in lesson 9. So let's begin with problem 1. So we do know that an exponential function has a form ab to the power x. Now, we have to respond to these questions. A, the variable x represents the input. F of x, of course, it represents the output. Domain of f of x is all real numbers. Range is f of x is greater than 0. Initial value is a. The vertical intercept is 0a. And then what about the horizontal intercept? It's none. The equation of the horizontal asymptote is y equals 0. And then on the graphing grid below, draw an exponential growth function. In this case, what can you say about the growth factor, b? So let's say that b is greater than 1. If b is greater than 1, we know that then there is a growth factor, right? Right? From lesson 9. So the graph is going to be somewhat like that. It always has a J shape, right? Okay. Now, what about for a decay function? B should be greater than 0, but less than 1. And then, what about the graph? We're going to have like that. Okay, all right. Now let's go talk about growth and decay rate. Now, when you have an exponential, f of x equals ab to the x, we know that it's either a growing function or a growth function or a decay function. And it grows or decays at a constant percent rate, r. A constant percent rate, r. So r is either the growth rate or the decay rate. Now, it's usually should be in decimal form, but sometimes it's going to be in percent form or percentage form, and then you have to change to decimal. So to find your b when you have r, b is always going to be 1 plus r. Remember, it is a growth factor. B is a growth factor here, so it should be greater than 1. So you add your decimal, your r in decimal form to 1. Now, what about decay factor? That should be less than 1, but greater than 0. So you subtract the decay factor from it. Okay? And then if you have your b and you're trying to find your r, if it's growth and then if it's decay. But I think if you remember, this, it should be fine, right? If you have this, you don't have to, memorize all four. If you know that my growth rate is 1 plus r, my decay rate is 1 minus r, you should be fine, okay? Now let's go to the table. So let's look at these exponentials. Now for the first one, we have y equals 812 times 0.71 to the power t. Because b is less than 1, this is a decay. The initial value is 812. The growth or decay factor is 0.71. The decay factor. Now, what is R, the rate, the decay rate? What is R, the decay rate? Remember, when it's a decay, you have B equals 1 minus R. So B is 0.71. So R is going to be 0.29. You could always solve the equation, 0.29. Because both of them should add to give you 1, right? When it's a decay, it's a decayed function. All right. So what is the decay rate in percentage going to be? Is 29%. Now, what about the second one? This is a growth function because b is greater than 1. So you do growth. And then the initial value is 64.5. The b is 1.32. Now, we know that the decay rate, because this is an increasing or a growth function, is 1 plus r, so it's 0.32. And then we have 32%. Okay. Now let's look at the next one. Here we have that the function is a growth function, and then the initial value is 8.24. Now the growth rate percentage is 0.5%. Now we are supposed to fill in the blanks. Now if you want to start from the percentage, the percentage of the rate, then remember 0.5%. Here you have to take your time. 0.5% is not 5 over 100, it's 0.5 over 100. And if you put this in your calculator, you should get that 0.005, okay? So remember, we are looking at a growth rate. So if this is our R, then B is going to be 1 plus R, which is 1.005. So I put it in here, 1.005. And then our R in decimal form is 0.005. And that's it. So Y equals, it's a growth, so 8.45. And then our B is 1.005 to the power 2. Now the last one, we have the rate in percentage 20%, but it's a decay, right? So B equals 1 minus R. 20% is 0.20 or 0.2, so B equals 1 minus 0.2, B equals 0.8. So this is 0.2, and this is going to be 0.8. So I have 150 times 0.8 equals Y. And that's it. So these are worked examples. You could just try to see if you understand them or you go over them. in your notebook. Um, and then there are more examples here. So this is a decay. Initial value is 300. Our B is 0.88. Our R is, because it's a decay, B is 1 minus R. So if you solve that, R is going to be, so this plus B plus R should give you 1. So this should be 0.12, and this should be 12%. Now for the next one, you're going to have a growth 213 for the initial value, 1.2, 0.2, 20%. For the next one, we have 9.8% here, but it says it's a growth, right? So our B, let's start with our R. 9.8% is 0.098. Okay, so 0.098, and because this is a growth, we're going to get 1 plus, or 1 plus 0.098. So that gives us that, and this should be y. F of t equals 177 times 1.098 to the power c. Now the next one, we're going to have a decay. Now the initial value is 5.41, but the decay rate is 7%. So 1 minus 7% is 0.07. 1 minus 0.07 is 0.93. So this becomes our B, 0.993, sorry, 93. So this becomes F of t equals 5.41 times 0.93 to the power c. All right. Now this is a media example, so please try to watch it, but I'm just going to go over it real quick, and then I'll have you finish it by going back and then watching it. So in 2001, the population of a particular city was, so in 2001, the population of a particular city was 22,395, with an identified growth rate of 6.2% per year. Assume that this growth rate is constant from year to year. Write an exponential growth model for this situation. So in 2001, that is our starting year or initial year, the population was 22,395. So my P of t is going to be A, which is 22,395. And then our growth rate, R, is 6.2%, which will be 0.062%, right? If you divide that by 100, 6.2 divided by 100. So this would give me 1.062 to the power c. That's it. Now, what is the approximate population of the city in 2006? Now, our starting year is 2001. So the way you should see it is that if I'm born in 2001, or if someone is born in 2001, how old was that person in 2006? 5 years. So 2006, t equals 5. We are going to have P of t equals Okay. And this should give us 30,253.36. And then because we are dealing with population, you do 30,253. That's it. Because you don't want it to go over, right? So you don't want to round up or just round to the nearest whole year, whatever. Just do that. 30,253. All right. Now, estimate the number of years it will take the population to double. So we are looking at a doubling, right? A doubling. Now, we started with 22,395. So 22,395 times 2, this should give us 44,790. Okay? So this is the doubling population. So we were trying to find what year the population will double. So what we are going to do is that we're going to pick 44,000 as our y is equal to the function y2, y1. And then you go to the calculator and then you do it there. And then you find your time. All right. There is a video on this. Please watch the video. Okay. Please watch the video. And at this point, you should be able to do this on the calculator. So when you do that, your t, if you do your second trace and intersection, enter, you're going to have 11.52. It says round to the nearest whole year. So you're going to get what? 12 years. 12 years. So 12 years means from 2001, 12 years is going to be 2013. And then draw the graph in the book. Draw the graph in the book. If you're struggling, go to the video. Please go to the video. All right. Oops. So this is a worked example. I'm going to skip that. And then let's look at this one. So this is a you try problem. So I'm going to go over that. This is problem 7. So after graduating from college in 2010, Sarah accepts a job that pays $52,000 per year. At the end of each year, she expects to receive a 3% increase or raise. 3% raise. Let T represent the number of years. Write the exponential growth model. S of T, that models her annual salary given the information above. So first of all, what is the initial salary? It's 52,000. Now, what is the growth rate here? Is as a decimal, it's 3%. As a decimal, it's 0.03. What is the growth factor? Because there is a growth rate, you know you are adding, right? It should be more than 1. Now write the model. So we have 52,000. That's our A. We have 1.03. And then we have, of course, you could start with S of T. But I guess you don't have to because it's already set up here. Now, B says, if Sarah's salary continues to increase at a rate of 3% each year, determine how much she would make in 2015. So we started from 2010. Now 2010 to 2015. In 2015, that is 5 years, right? 5 years. So you want to do S of 5 equals 52,000, 1.03 to the power 5, and that should give you 104,000. Oops, no, That should give you 60,000, 282,000. I mean $282.25. All right. C. How many years will she have to work before her salary doubles? Okay. So in 2010, the salary was 52,000. So if you're looking at a doubling, you are multiplying by 2 or you're adding another one, which gives you 104,000. So how many years is it going to take? Again, you have to use the calculator. So you have 104,000 equals, and then you have 52,000, 1.03. Now, when you have these type of questions, the first one I didn't do it, but this I'm going to solve it. So you should, first of all, I mean, you could put these in the calculator as y1, y2, or you could fix it a little bit before you go to the calculator. Okay. Now, if you keep it as this, it's fine. But if you want to fix it a little bit, you could also do that. Now, what do I mean by that? You could divide both sides, right? By 52,000 and then 52,000. So you're going to have, this will cancel that. You have 2 equals 1.03 to the power x or t. You see that? So let's go to the calculator and see what we are going to get with this or from this. So I'm going to go to y equals and erase that. And then I'm going to put in my y1 was 52,000. I'm just going to do it the bigger way first. And then times 1.03 to the power x. And then we have 104,000. Now, if I go to my window, because this is a practical problem, I'm going to do 0 to, let's do 0 to 50 for x, which is my time, right? And then for my y, those are going to be very big values. So remember, our initial is 52,000, so we might as well start from 50,000. And then it goes to, let's do 125,000. Look at what I have. Wow. So it's all about setting up your window right. Second trace, 5, enter, enter, enter. What do we have? 23.45. 23.45 for x. 23.45 for x. That's what we have. 23.45 for x. Now, because you want to round up, in this situation, remember that because you are in the 24th year, right? You are in the 24th year, 23 point something. So you say 24 years, 24 years, 24 years. So from 2010, in 24 years, you're looking at 2034, right? 2034. All right. Now, let's use the second approach, what I talked about. So if you have y1, and then remember, we canceled, so we had that. And then here for y2, we had 2. So we would have to change the window. Let's just do maybe a standard window and see what we're going to get. Oops. Or maybe before we go to the next problem, let me just try it one more time. Let's look at our graph. The graph doesn't look that nice because the numbers are very low. It doesn't look that nice because the numbers are very low. But let's just try second trace and see. 5, enter, enter, enter. Oh yeah, we got the same thing. We've got the same thing. So even though it didn't look that nice, we still got the same thing. And I think that is great. All right, so that's another way you could do this. So I'm going to try to just fix my window and then see what, yeah, I know I got the value, but I'm just going to try to see if I can fix the window. So let's see. So looking at how it's set up, I'm just going to do 0 to 50 here and then see what I have. Okay, it's still down. No, I think the problem is my y. The y is too big because I decreased the y so much. So I'm going to do 0 to 20. Let's see what I'm going to get here. Oh, now it's getting better. Oh yeah, so I'm going to decrease this date to 5. Let's see. Oh yeah, so now it's better. So, but I think because with this you struggle with the window like I was, it's better to stick with the big numbers, but you get the same thing in the end. All right. So that is it for that. So doubling equation, you have that as 104,000 e equals 52,000, 1.03 to the power c. Okay, and then this is 24 years, or 24 years, or 2000, what was it, 34? Something like that, yeah, 2034. And that's it, okay? Again, for the window, remember, it's a try and error, right? So you have to know how to fix it, and that's it. All right. Now let's go to the next problem. This is a media example. So I'm going to skip this. So please try to watch this in the media lessons, okay? Now let's look at problem 10. This is a you try problem. So let's go look at it. So in 1970, Buffalo, New York, had a population of 462,768 people. Now, assume that the population decreased by 1.4% each year from 1970 to 2030. Let T represent the number of years since 1970. So in 1970, T equals 0. Write the exponential decay function that models the annual population given the information below or above. Okay, now what is the initial population? It's 462,768. What is the decay rate? The decay rate is 1.4% as a decimal, which will be 0.014. Okay. Now determine the growth factor. Remember, it's 1 minus R. So that gives us 0. So B is going to be 0.986. 0.986. So your model is going to be 462,768, 0.986 to the power t. Okay, now B says if the population continues to decrease at the rate above, determine how many people lived in Buffalo in 1989. Now in 1989, if someone was born in 1970, in 1989, that person is going to be 19 years. 19 years. So you're going to have p of 19, put it in the equation. To the power 19. And that should give us 354,000. Remember, it's decreasing, so .48. But again, the 0.48 goes away, so you have that. Okay. And what about C? Now C says, how many years will it take for buffalo population to decrease to half what it was in 1970? So halving equation, that's what you're trying to find. Now in 1970, the population was 462,768. So you divide that by 2, and what do you have? You're going to have 231,384. Okay, so you equate this to the function, and then we see what you're going to get. So if you do that, you're going to have 231,384 equals 462,768, 0.968986 to the power t. That's it. So y2, y1. And then you solve for t. So let's go do that. So we go to y equals, and then we erase that. So y1 is 462,768, sorry, times 0 point or 0.986 raised to the power x. And then here we have 231,384. And then our window, we have 0 to, let's do 0 to 50 or 0 to 100. But maybe it might be a long time for that to happen. And then here we have, let's do 480,000 and go to graph. Oh yeah. So second, trace, 5, enter, enter, enter. Oh yeah, we've got 49.16. So we are in the 50th year, right? So it's going to take 50 years. 50 years to do that. 50 years to do that. Now, let's say that because I have a halving time, I had 384 equals 462,768 or 786. Oh yeah, 768, 0.986 to the power t. Now I could divide this by 462,768 and divide that by the same thing. Now this is going to give me 0.5 to be equal to 0.986 to the power t. So you could use this as we did for the first one. So you go to y equals, then you're going to delete this. And then here, you're going to have 0.5. Now the window, of course, should change. So I'm going to do 0 to that, 100. I think the problem with the first one is that, remember, the x is going to be time, so it's not going to change, while the y is what is affected, so the y should be a little low. And then let's go to graph. Okay, so this it's kind of better, but we could do more on that. So let's see, 50 graph. Okay, it's going down. So y, so x is that of window. So we do 5 here, we do 60 here. Yep, yep, now it's getting better, right? Now it's getting better. So at this point, you could just, yeah, do second trace, and then 5, enter, enter, enter. Yep, and then you get your same value. Okay, so that is another way to do this as well. All right. So we have 50 years. So it's going to happen in 50 years. So in 50 years from 1970, that is 2020. That is 3 years ago, 2020. 2020. Okay? All right. Now, the last part of lesson 10 is exponential regression. Again, same regression from what we started with. Now, 11 is a media example, so you want to watch it. But again, same thing. You put in your table values. So here it says you have this table. Determine the exponential regression equations that models the data below. So write the exponential regression equation in the form y equals ab to the x and then pt equals ab to the t. So first of all, you have to enter your values. So let's do that. So this is problem 12. So we're going to do that. So our values, we go to the calculator and then put it in. I want to make sure I have everything right before I go to the calculator. So I'm going to go second mode, quit, and then I go to start, edit. Now I'm going to go up and then erase everything and come down. And then over here too, I'm going to do the same thing, and then come down. So, oops, I thought I was sharing my calculator, not yet. Okay. So I'm going to I have to put in the values now. So my values are going to be, so for L1 or my X or T, I have 0, enter, 1, enter, 2, enter, 4, enter, 6, enter, 9, enter, 12, enter, 16, enter. And then I go to my Y values. You have 125, enter, 75, enter, 50, enter, 32, enter, 22, enter, 16, enter, 10, enter, 5.7, enter. So these are my values. Now, so I'm trying to find my my exponential regression equation. So I could go start before going to the graph and go to calculate. And then I'm going to go down, 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 down. Oh yeah, there it is. Exponential regression. Enter, 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 enter. Now, if you want to store the equation in y, you could do that. But for now, I don't want to do that. So enter, enter. Oh yeah. So b is 0.83669. So that is a decreasing or decay function. And then my a is 82.943. Now, we have to go back and then put it in, just like we did for quadratic and linear and all those. So here, we could do for 83, remember, a is the initial value. So we are just going to round. So we're going to get 83 for that. So 83. And then for b, we could do 3 decimal places. Now it tells us that we should round the final, it says round a to 1 decimal place. So if we do that, I mean, we have 82.9 Yeah, 82.9. And then round B to 3 decimal places. It says it on there. So we would go back and then put it in. So we're going to have 0.837. So y equals, right? Y equals, and then x. Now here we're going to have P of t equals, again, same thing. To the power t. Okay. Now it says generate a scatter plot for this data. Remember scatter plots? So we have to go back to our calculator. Now we could just go back and install this, right? Oops. We could just go back and install this. Now I'm going to go start again, calculate, and then 0, and then enter, enter, enter. Oops. Enter. Let's do it again. What am I doing? Start, calculate, oops, calculate, and then you go 0, enter, enter, enter. Now here you could store the equation, so 1, then you do y1, and then enter, enter. So you know when you go to y, you're going to have that, right? So here you're going to erase this. And then because we need a scatter plot, you have to put that in here. Plot 1, then come back down, go to graph, and let's see what we got for the graph. This is what we have. I think we have a problem. So you have to go back and then check what is going on with it. Plot 1, down. And then we could do 0 here. Go to graph. Still don't have it. See what is wrong with it. Oops. So you go to start again. Calculate. And then you do 0. Enter, enter, enter. Vars. Y vars. 1. Enter. And then you do that. And now, okay, I see why it's doing that. It's because of my window. Yep, so I have to fix my window. That was the problem, because the window is in a mess. So I have to fix that. So that was the problem. So 0 to 20. Look at my x value. So I do 0 to 20 here. And then for y, I'm going to do, remember y starts from, let's see, the 5.7. So we could do 0 to, oh, I had 0 to 5. That's terrible. 130. And then go to that again. Now I'm going to erase this and go to graph. Now I have it. Okay, so I think it was my window. So you should know that sometimes these things can happen to you. All right, so you draw this on your in your space there, right, in the box. And then remember the window, set up your window. Now the next question is going to say that what is the rate of decay as percentage for that. So the rate of decay, remember, is going to be 1 minus 0.837. That's what we got, right? So that gives you 0.163, and 0.163 is 16.3%. So you have that 16.3%, and that's it. Now determine P of 20. Now again, you're going to use your model. So don't go to the table, use your model. So P of 20 is going to be 82.9, 0.837 to the power 20. And that should give us, I think, approximately 2.36, something like that. 2.36. It says round to two decimal places, so that's what we're going to do, 2.36. No, that's P of 20. Use your equation from part A, determine T when P of T equals 28. So here, you're trying to find the time. So P of T, we know that that is 82.9, 0.837 to the power T equals 28. And that's what you're going to have. All right. So you could put this in a calculator, y1, y2, and then solve for t. Now, if you do that, you're going to get 6. Let's do that on the calculator. Let's do that on the calculator. So if you do that, you're going to have y equals, erase that. So y1 was 82.9. Now remember, my plot is on, so I do not have to forget that. And then I had 0.837. Raised to the power x. Oops. And then for y2, I have 28. Then go up, then take the plot off because I'm done with it. Come down, and then go to graph. This is what I have. Second trace, 5, enter, enter, enter. So I have 6.1, 6.10, 6.10 for that. Okay, 6.10 for that one. And that's it. That's all you do. I think that's the end of that problem. Yep, that's the end. And then there is a last problem here, and that. So you have investment V in thousands of dollars after n years. So use your calculator to determine the regression equation, the exponential regression equation. So again, you go to your calculator, go to Stats, Edit. We're going to erase everything. So now we're going to put in the x values. Just 0, enter, 3, enter, 5, enter, 10, enter, 15, enter, 22, enter. And here we're going to have 4.63, enter, 5.92, enter, 6.88, enter, 10.23, enter, 15.21, enter, 26.39, enter. So this is what we have. Now I'm going to go, I'm going to go Start again. So let's just forget about this. Start again. And then calculate. I go to 0. Enter, 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 enter. Oh, so this is what I have. So my V investment of T is going to be, so A, let's say I do one decimal place for A, 4.6, and then B, 3 decimal places. And that's what I have for that. Okay, 4.6. So that's my regression equation. That's my regression equation. That's what I have for the regression equation. It says round A to 2 decimal places, so we have 4.64. Okay, 4.64. Now B says, what is the percent rate in the value of this investment? What percent rate is the value of this investment increasing each year? Remember, it's increasing. Why do I know it's increasing? Because B was 1.082. So B is 1.082. So R is going to be this part. R is 0.082, which is 8.2%. 8.2%. Now C says determine V of 12. So V of 12, you put that in this, so you have 4.64, 1.082 to the power 12, and this should give us 11.95. Remember, V is in thousands of dollars, so $11,950, which is going to be $11,950. What did I do? I multiplied by 1,000. Multiplied by 1,000. D says, how long will it take for the value of the investment to reach 100,000? So if you want to know that, it's 100,000 is our Y. And then we have 4.64. Y1, Y2. Okay? So you go back to the calculator, and then you do that. Now you should have T should be equal to 38.98 if you do the intersection on the calculator. So that should give us 38.96 years, which is 39 years, right? So it would take 38.96 years, or approximately 39 years, to reach 100,000. All right. How long, E says, how long would it take for the value of the initial investment to double? So the initial investment, what was the initial investment? It was, let me check that. It was 4.63, right? Yeah. Yes, it was 4.63. So 4.63 times 2, because it says how long will it take it to double. So that will give us, or 4.63 plus 4.63. You got a 6 here, you got a 2 here, and then you've got a 9. So 9.26. So how long will it take for it to double? So you have 9.26 equals 4.64, 1.082 to the power T. So Y1, Y2. So let's do that on the calculator and see what we got. This is the last problem, so let's erase that. And then let's put in, so our Y1 is going to be 4.64. Okay, yes. I think the investment was 4.64, right? 4.64. Let me go back and correct that. 4.64. 4.64. From the model, right? From the model is 4.64. So this would be 9.28 for doubling. Yep. So 9.28. So let's go do that. Right? So because from the model, that's what we are using. So we're going to have y1 is 4.64, and then we have the parentheses 1.082. We close that to the power x, and then here you have the doubling amount. Oops. 9.28. Now you could go to window and then change your window. So we have 0 to 20, but we're going to increase that to 0 to 25. And then here we're going to have, remember the initial value, the lowest value is 4.63. So we're going to do 4, 2, 4, 2, 30. And we're going to go to graph. Second, trace, 5. So these are small numbers, so I'm not worried about, doing what I did initially where I divide. No, so these are small numbers. So in the end, you have 8.79, which is 8.8. So it would take about 8.8 years, or approximately 9 years, for this investment to double. So that's it for lesson 10. I hope you enjoyed it. Please send me your questions, and yeah, I would get back to you. Thank you.